Hi, everyone.
They're saying hi virtually. Susie's from England, so she's late at night there.
It's early evening. It's just actually getting dark, which is quite a thing because I'm aware that it's not like that for everyone. But yes, hello, everyone. And it's great to be here. It's very exciting. So I'm just going to start, shall I? Now
Yeah, you look fabulous.
Oh, well, thank you. Thank you. Hi everyone, I'm Suzie. I'm a musician, not a scientist, but I'm absolutely passionate about particularly astronomy and particle physics are the two things that I'm really, really excited by. And this image here at the beginning, this is an image of the TUC 47 globular cluster, which contains a set of pulsars which feature in one of my pieces I'm going to talk to you about, the Tabulation of cosmic scintillation. So I am a musician and I write pieces of music that sort of represent, I guess, not scientific processes, but processes that have been discovered through the scientific inquiries. So I'd like us to consider the idea that the music is cosmos and the cosmos is music, and that the entire cosmos is a piece of music that is literally composing itself in each moment as it unfolds, so that you and me and our voices are all part of this rich and unending cosmic symphony. This is where my pieces are written, from this place. And this is not a very new idea, this is a really old idea. And how it's tended to be rationalized has been the cosmos has certain properties, like we observe phenomena to have certain properties, and music has these same properties. And so therefore they must in some way be linked. And so for the classical Greeks, and particularly for Pythagoras, where this idea comes from, and actually where we get our scale, the notes of the Western classical scale, they come from anecdotally Pythagoras. For them, astronomy, number, cosmos, music, they were all aspects of the same thing, and they related it through ratio. So because, for instance, you have a length and then you have a half, this was a really important thing for them. And in music, we have a length of string, and when we half it, we get an octave. And then they would observe the same kinds of ratios in the planetary movements. And for them, this was really significant fact that something very deep was going on. And I just want to show you actually some, if I can, and I'm not sure how, there we go. So this is some Greek notation music. If you look to the left, you can see that, well, I don't read Greek, but the Greek music is written in ratio. So this is an ancient Greek piece of music. And then it's been written in modern notation. You can see how different they are. We like to think of our pictures as existing in a space of up and down. We live in a really dimensional place with our music. And for the Greeks, it was the relationships between the sounds that was important to them. And then for Johannes Kepler, ratio was really important for him too. But he gets there from the regular solid figures, which is an ancient Greek idea. But he's talking about the harmonic relationship between the ratios. He describes it as harmonic, and he says that the planetary movements, the simple consonances have been expressed, and that all those consonants which are present in song are also found in the heavens. So here he's saying there's a human element, like the songs that human beings sing. So the music of human beings, and I'm aware I'm playing very like Western classical harmonies, but this is where Kepler is working from, is also present in the movements of the planets. And so he's working from this idea that these things are musical. And he actually goes so far as to ascribe music to the planets. So you can see Saturn here has got its little tune, and you can see Jupiter has a tune. And what's really interesting, I'm just going to draw your attention to Saturn and Jupiter, is that Saturn is a major tune, and Jupiter's exactly the same, but it's a minor. I really love the fact that it just looks so similar and the sound world is so different. So he's coming at it from the idea that the planets are musical, but he's going to impose a human element onto that. Whereas looking at the idea that ratio is somehow some kind of cosmic truth that is emerging in these different places. And what's really interesting as well is to notice that actually it's not till the 19th and 20th century that composers start to get interested in what scientists are doing and start to look at discoveries and go, oh my God, there's something inherently musical here, and actually start to compose pieces of music that look at that. So Charles Ives writes his Third Symphony. It's like a universe symphony, and it only exists in like fragments of notes, but he's trying to encapsulate like all the cosmic processes in musical instruments. And then Stockhausen starts to write a lot of music that really tries to get at the roots of music and the cosmos. And one of his pieces, Ylem, which is it's the story of cosmic evolution, starting with the Big Bang, and then everything, the universe expanding, and then contracting back into a big crunch, which, you know, is one theory, the idea of the universe gravitationally pulling itself back into itself, coming back into a crunch, and then going out and coming back in. And in this piece, he assigns pitches to the performers, and they start in the center of a space, and then they start playing these pitches really, really loudly. And then they start to move out of the space slowly. And as the universe expands, which is represented by their movements, the pitches start to slow down until you just end up with these little points, which I guess could be stars or galaxies or whatever. And then the performers start to come back into the space. So he's exploring these ideas through movement and sound and the relationship to things in a space. And perhaps prior to the 20th century, the only instrument that really explores this is actually the Pythagorean monochord, which is just a sort of a piece of string, which is a fundamental note. And then you can explore the harmonic series, the idea that I was saying before, this ratio. We can put the string in half, and then we can put the string into a third and listen to the notes that come out. So I just want us to think a little bit about our definition of music. And I don't want to explore the right answers. I don't think there is a right answer to this, but just to think about what music is for us as human beings and what actually is music. I think it's a really interesting question I constantly ask myself. And so in this quote, we've got John Cage saying, music is everywhere, you just have to have the ears to hear it. So there's something about a human experience for John Cage. And actually he invites us to consider that sounds outside the realm of composed music is also music, which is where we start to get to the idea of the universe is a piece of music composing itself. Because John Cage's art is about saying, well, we don't necessarily need to have a human being composing something. And he writes a very famous piece, I'm sure you've heard of, called 4 minutes 33, where the only instruction is for the instrumentist to play tacit is to not play. And what this allows is for the sounds that emerge during the time frame of the piece, 4 minutes and 33, suddenly become at the center. We suddenly are able to notice them and appreciate them. And they're usually obscured by, of course, the content of the written music. And another American composer called Lamont Young, in the 60s, he starts writing pieces devoid of what might be called the musical content, but are pieces of music nonetheless. And one of them, Composition 1960, number 10, Draw a Straight Line and Follow It, or Composition number 6, 1960, number 2, which is Build a Fire in Front of the Audience, which are all about events unfolding in time. And then we have this definition from John Stevens' book, Search and Reflect, which is about sound and silence. And then the sounds have to somehow have some kind of duration of length. And I love the click and sustain because it reminds me of the pulsars. I think he neglects to talk about something happening through time here, but you can see there's a little arrow moving down the bottom, or this way in fact, that sort of alludes to this idea that this process is unfolding in time. So for us with music and cosmology, the definition that we can start to use is that music is events that unfold over time, over a period of time, and that those events are defined in relation to one another, and that these events can be determined by something like a physical law or a musical law. So the events are something like vibrations or frequencies or movements, and that they're shaped by physical laws. The music itself is applied physics. There's a narrative, something is happening, and it's defined and shaped by something. They're physical laws, musical laws, or musical laws that are like shaped by the dominant culture. But the events are unfolding according to something. And this is similar of the universe and the things that we've observed, you know, our laws of physics. When we look at what's going on, when we observe things, and then we ascribe we observe patterns, and then they become our physical laws, and they in themselves actually unfold and change over time. So the human voice, to bring us back a little bit, gives us this beautiful meeting point, an opportunity or a conduit or a switch to explore the inner states of ourselves and the outer states of ourselves in the universe. The astronomer Carl Sagan, he talked a lot about in his book Cosmos, the idea that we're a way for the universe to know ourselves. We're conscious beings, and that we're embedded further in space-time. So, and Lee Smolin, in his work with philosopher Roberto Mangabeira Unger, he argues that the human experience of the universe has to be incorporated into any meaningful theory about the nature of the universe. And then we're starting to develop loop quantum gravity. We're starting to develop a theory of gravity in which we're a part of it. And so our voices are also a part of it. Us as human beings, we're singing with the cosmos as it is singing when we are singing. So when we sing a sound, we're investigating the inner sound world of ourselves, the sound also though as it travels out. So the power of our voice is that it connects us to cosmic processes in this really deep and profound way, that we're embedded in the fabric of space-time. In each moment and gesture we make is enmeshed inescapably with space-time and quantum phenomena. So when we think, there are quantum processes going on. So when we even decide to sing, like, is the space-time making us sing? Is it the movements and fluctuations at these very, very tiny levels that we're not consciously aware of? Or is it us that are then affecting? So there's this sort of constant feedback. So music and our voices also connect us deeply to time as well. Music, remember, is unfolding in time. So we may not really understand what time is, but when we sing, we can connect ourselves directly to the expression of sound in time, to our own experience of time. And that music then shapes our experience of time also. So we enter this relativistic field where each and everyone's experiences of the timescape that they're in will be different depending on their own point of view. And the power of the voice, of course, is it's immediate and accessible to everyone, unlike learning to play an instrument, but I'm sure you're all very aware of that. So even when we sing a note and we follow the entire trajectory of this note from start to end as it rides along our breath, this note speaks to or relates in some way even to the evolution of the universe itself. So we could say that the universe, our theories say, start in this Big Bang, which then as it evolves, it changes through time. So even when we sing just one note for ourselves, our note is like an allegory for the creation of the universe. We start to sing it from nothing, and then the note changes and evolves as the breath moves through our body. So the note itself is even like telling the story of cosmic evolution. So our physical theories, objects with forces. So we have objects in space and the rules that say this object is going to move like this. And in music, we have exactly the same. We have the pitches or the sounds, and then we have the ideas that shape exactly how those things can move in idiomatic music. For instance, you know, the songs that we're all exploring, they have this sort of internal logic to themselves. You know, there's ways in which they can move. So these are the ways music relate to sort of classical theories, and quantum theories relate, I would say, most strongly to things like free improvisation, where it's possible to explore chance and aleatoric structures. Non-locality and entanglement can all be explored in a freely improvised musical structure. So, how does this relate to the music that I write? Well, the first piece I think I've probably only got time to talk to you about is called A Tintinnabulation of Cosmic Scintillation. And a tintinnabulation is, thank you very much. A tintinnabulation is, it's about bells ringing, but Arvo Pärt uses it when you have one chord and you're selecting notes out of that chord. And this piece is about pulsars and pulsar detection. So the Tuck 47 image is where these particular pulsars are. And pulsars are neutron stars, and there was an image just a little while back. And they are incredibly dense forms of matter that have beams of magnetic radiation and radio waves coming out of them, a bit like a lighthouse, and they rotate incredibly quickly because the forces that have created them mean that they are spinning really fast. And some of them, think back to John Stevens' diagram, will click. They'll have rates that, you know, are 1 per second or 2 per second. So they'll be clicking sounds. And then others will be spinning so quickly that they can be realized as pitches. And within the Tuck 47 constellation, there are 23 pulsars I think we've detected, and we have sound resolutions for. And when I created this piece, we only had resolutions for 16 of them. So I actually need to update it, which I absolutely love that I did. The science has moved on since I've written this piece, and I have to go back and re-edit it. So these pictures correspond to the pulsars' rotation rates, basically. They're rotating so quickly that one of them produces a note that's an F. Now, what I've done is cheat slightly because it's not exactly an F. It's, you know, they're not exactly, the pulsars don't know about the Western scale, chromatic scale. So I've cheated a little bit, but the way the piece is structured, the notes are never sung exactly in tune. They're never performed exactly in tune. So the pulsars that are in this cluster constantly spinning can be thought of as constantly singing. They're constantly singing this chord. All the time. However, when signals from the pulsars travel through space towards the Earth for us to detect, they get disturbed by cosmic debris and bits of, you know, stars, things in the galaxies, all the, well, not so much galaxy, because Tuck 47 actually goes around our galaxy, the Milky Way. However, there's all sorts of things in the way. So the signals don't come to us as 16 sounds all at once. They scintillate. So we'll get one and then it'll get disturbed and then it'll come back in. And so for us on Earth, when we detect this, what it means is we have this chord that's constantly shifting and constantly changing. And when we take this process and we move it into a piece of music, this is what the tintinnabulation is. And so the piece title, it seems very long, but it's describing exactly what's going on. The chord is constantly shifting and changing. It's cosmic scintillation, but it's the tintinnabulation part. It's the fact that the chord keeps shifting. And so I scored the pitches out and then I wrote a set of instructions. And I think we probably need to finish fairly soon. But if we could finish by playing the piece of music, that would be amazing. And I'm not sure how to make that happen. Oh. Here it is.
Hey, Suzie.
Hi.
Hi.
Hi, Tiffany.
Hi.
Hi.
We have some very interesting questions for you. I know we had to kind of cut you off a little bit there, but
That's okay.
I thought it was amazing. We have one comment that says, wow, so beautifully weird and mesmerizing, from Sarah Nixick, who is actually going to be talking tomorrow. And I think the two of you might really enjoy each other. So she's going to talk to us about the vocal calls of whales. And I think you two might really enjoy each other's company. Some of the other comments that we have, Jessica said that there's a climatologist out in Seattle, Washington in the States named Judy Tweed. And she actually is basically creating a similar musical production based upon the changing Arctic Sea and the changes in temperature and how they relate to musical harmonics. And Larry said that he actually has a song called Music of the Spheres, which I've listened to. And a last comment that we had, Walter actually says, what a great history of STEM songs, like literally a great history. And then, Jessica says she's going to send the Judy's TED Talk to me and I can get it to you.
Oh, great. Well, actually, there's a TED Talk I wanted to talk about in my talk, which I didn't. So my talk was action-packed. It was information-packed, and I didn't even get to share many of my pieces, actually. So, but I'm happy to talk to anyone if they want to about the rest of the pieces I have and the rest of my work, because I have more, obviously. But
yeah, you and I are going to start to collaborate a little bit on electron configuration. So I'll leave it with that. With Suzie's future project is going to be to maybe make a soundscape of the light emissions that come off of electrons. So thanks, Suzie. We appreciate you coming all the way from England.
Thank you.
And I think everybody knows how I assumed that maybe you were a particle physicist because you know your stuff. It's pretty amazing. So yeah, we're going to turn it over.